When you can fit incredible power into a tiny space, you have a choice to make. You can become a genie, which would be cool if it wasn't impossible, or you can become a power electronics guru, which is only slightly easier than becoming a genie. Michael Laughlin could have done either, but thankfully he picked a role in power and is here to share his wisdom with us and talk about what he's doing with Intel's Enpirion power products. Welcome to Tech Chats, Michael.
All right. Thank you very much. I am really excited to be able to sit down and talk with you about our digital power products.
Okay, so now let's talk about your Enpirion power solutions. What are you doing to help designers?
We've developed this family of digital power products to solve a number of very difficult problems that our customers tend to face. Those problems include, limited board space or high reliability as a requirement in their application. With FPGAs in general, especially as we get to higher and higher performance FPGAs, the tolerance windows are very tight. When you start talking about high-speed transceiver, the noise sensitivity is quite high, so the power supplies have to be optimized for that. Big problem that customers face is that they don't have a lot of time to get their products to market. And so using a digital power SoC is a very easy way to power your device in a very short period of time because it's a fully integrated solution. There's very little additional work that has to be done. And of course, you need high efficiency, and you want to know that it's going to work with the device you're powering. So in the case of, an Intel FPGA or an Intel ASIC, very often the ASIC development board or the FPGA development board is powered by Intel Enpirion power. And so we know from experience that it will work. The other thing that we're bringing into play here is that with the Intel FPGAs and Intel ASICs, we engage with those silicon design teams at a very early stage to get a complete understanding of their power requirements so that by the time their solution rolls out, we have the optimized power solution to go along with that, purpose-built from the beginning.
Okay, and you mentioned that these are fully integrated. So what exactly do designers get with an Enpirion power SoC?
Well, let me add just a touch of history here to this. What you get is an integrated solution that includes the controller, in this case, a digital controller, the power MOSFET switches, and the inductor, and a large number of the required onboard passives that you would use for decoupling, high frequency noise, and things like that. So the story starts way back in Bell Labs in the 1990s, back when Lucent was in the power business. The intent of the design from the beginning was small solution size, low part count, and high reliability, and of course high efficiency and all the things that go with that. So we're bringing to bear here a technology development that has spanned more than 2 decades and many hundreds of millions of dollars of R&D with the specific focus from the beginning of providing these very small, easy to use, and high performance and high reliability solutions.
And you've shown some different offerings and what they're designed to power in an FPGA or an ASIC. Why are the different feature sets important for how you have them broken out?
When you look at powering a device like an ASIC or an FPGA, there are, different power rail groupings have different requirements, and that's the intent of this diagram is to show that, when all is said and done, there's really core power with its unique set of requirements, transceiver with a separate unique set of requirements, and then kind of a catch-all group for the other supplies that aren't really, where the tolerances or things like that aren't very strict. So when you look at the core voltage rails, this typically you need a digital bus of some kind if you're implementing any sort of voltage scaling or voltage positioning. In the case of the Intel FPGA, what we call smart vid. You want very high accuracy because there's typically a lot of current gets drawn on these rails. And the tighter that accuracy, the lower you can operate within your tolerance window. And the power savings you get from that is a function of the square of that voltage difference. So their accuracy is important for power savings reasons. When we move over to transceiver, here it's all about ripple noise and the transients that you get from load steps. So there you want to have a very high bandwidth control loop. At the same time, you want to have very low switching ripple. And so that's what's unique about transceiver. And then the other rails, typically you want to focus on size and cost, and that's what we've done with this.
Okay. And earlier you mentioned and you emphasized that this is a digital controller that's being used. So how does that differ from the typical analog or pin strapping designs?
Okay, that's a great question. In the analog world, you have just a proportional or whatever it might be response to a change in the output that gets fed back and compared to a reference, and then something gets adjusted. Usually it's duty cycle, could be frequency, could be different, depending on the topology. In the digital world, you have a lot of things available to you that you don't have in the analog world. You can implement nonlinear loops. You can implement multi-state loops, which in this case is what we do. And then you can also do things like if you have a high enough sampling rate, like in these product families, you can respond within the switch cycle. Typically in the analog world, the loop doesn't respond till the next switching cycle that comes along. In the digital domain, you can respond within that switch cycle. So talking about the digital power SoC product family in particular, moving away from the benefits of what a digital loop versus an analog gives you, is that with the digital power SoC, you get the ability to fully configure the device. So you can go in, depending on the use application, you can program the input volt or the output voltage. You can set up your startup times and shutdown times depending on the power sequencing requirements of the device you're powering. You can configure the control loop so that you can use fewer capacitors if you're trying to reduce BOM and cost, or you can adjust the compensation for a higher performance loop with potentially more capacitance. It just allows you to configure in many different ways the way the power, the power SoC behaves. While it's operating, you can look at real-time telemetry. You can read back what your current is, what your voltage is, what your temperature is. And you can read back in the event of a warning or a fault, you can read back the status registers, from the device to understand where the warnings might be coming from, what operating condition you're in that might be causing trouble. Now, typically you do this during prototyping, but it's also valuable in real-time operation out in the field. Your board manager can log these faults, and then they can go in and make adjustments to how the device is operated. Another part of the configuration is programming the protections. So you can set, again, depending on the application, you can set your input voltage over voltage level protection level or under voltage protection levels. You can set output over voltage or under voltage levels. You can set temperature, fault and warning thresholds. You can set current or over current warnings and fault thresholds. It's really quite nice to be able to go in and set all of these things that with an analog device, you might have a pin to adjust some of these things, but typically you would have to go in and modify the silicon and create a completely new part number, and with all of the time and expense and inventory issues that entails.
Earlier you mentioned that you work with the Intel FPGA and ASIC silicon designers early on to get your power requirements right. That's a pretty broad family. Can you talk a bit about the capabilities that you have across the Enpirion line, and maybe what other applications or what other situations designers would want to look at Enpirion?
In particular, this digital product family is focused on FPGAs and ASICs. Also very good for rails that you might find on certain GPUs and things like that. But from a design point of view, when we, go in and we develop the specification and then develop the product for these, we typically have an FPGA family in mind as the lead device. And typically with an FPGA, the tolerances are pretty tight, the requirements are pretty stiff. So if you can power an FPGA excellently, you can power an ASIC or any other device that might have those similar power rails and similar current requirements.
Can you explain how SmartVid works?
SmartVid is a way that Intel FPGAs are able to implement an energy savings capability based on transistor thresholds on a specific FPGA. So at the time of manufacture, they do some binning, and in that binning, they can determine, does this FPGA need, 0.81 volts to operate correctly and meet all timing closure, or can it operate at 0.79 volts? Or wherever it might be. So they set up these bins for it to operate at the lowest possible nominal operating voltage. And then as the device is operating based on temperature and other things, it may signal back to the power SoC that it needs to turn up or turn down the voltage. So it's a smart voltage ID or smart vid.
Some FPGAs draw a lot of current. What kind of current can a designer get out of one of these power SoCs?
So when you look at the family of power SoCs, digital power SoCs, and devices designed for higher current, so the digital power SoC family covers the range from approximately 10 amps up to 80 amps. And when we rate a power SoC and we say this is a 20 amp power SoC, typically this is the rated current over the operating temperature range. So up to 85 degrees C, for example, which is an advantage that our devices typically have. Our thermal impedances tend to be very good. There's some small derating when you get to the higher current ranges, just because there's only so much power you can dissipate in a package. When you get to currents that are higher than, at about 80 amps is where we think you start running out of gas with a power SoC. It doesn't make sense basically to have that much power concentrated in that small of a spot. It just makes the thermal design of your board very, very challenging. Using the same controller technology, the same digital controller technology, we also have a family of multi-phase devices that can then get you well up over the 200 amp or more range when you get into the very high performance ASICs and FPGAs. So when you look at the digital power SoC family in particular, what we have is the ability to provide a scalability that's necessary with FPGA in particular. With an FPGA, you don't know what your load current or what the current draw is going to be until you actually implement the image into that FPGA and power it up. So you rely on tools that are provided, things like an early power estimator that gives you a range of what the current is going to look like. And those can be, somewhat variable. You may end up in the end needing more current. You may end up requiring less current. Power estimators typically overestimate. So in the actual implementation, you can use less, a device with less current and hence save on cost. So what we have is the what we call the 2100 family. So EM2120 is 20 amps. 2130 is 30 amps and 2140 is 40 amps. Those are all footprint compatible. And this is really important for FPGAs is the scalability. And the same thing at the higher current. So EM2260 is a 60 amp device. EM2280 is an 80 amp device. Those are footprint compatible and fully interchangeable. You have the option to either scale up or scale down if you end up having, more or less current requirements in your, device when you actually get it in the lab.
Earlier, you mentioned that this has been something that's been developed over decades and with hundreds of millions in R&D rather than just being slapped together. Can you talk a bit more about what that development has included?
Yeah, so we have essentially 4 what I would call foundational pillars that have led us down the path that we're on. First of all, silicon expertise in particular high frequency LDMOS. So the high frequency allows for smaller inductors, fewer input and output filter capacitors. The way that works is that this LDMOS has a much lower switch loss for a given load current or process node than would a vertical MOS or VMOS. So we can operate at a higher switch frequency that where we would have the same efficiency as a vertical MOS device that would have to operate at a much lower frequency. Another key thing here is magnetics engineering capabilities. So we have on staff some of the premier magnetics experts in the world, and we design, formulate, and characterize our inductors for optimization in the operating conditions that the PowerSoC is designed for. If you were to go get an inductor from a mainstream supplier, that mainstream supplier would give you a data sheet, and that data sheet would have 3 or 4 or 5 key parameters at best. We characterize our inductors over probably 30 key parameters, over frequency, over temperature, over volt second stress, input output voltage combinations. And then we take all of that information and use that to optimize the control loop topology and performance characteristics to match exactly with that specific inductor. And then in the packaging world, so these operating at these higher switch frequencies, if you don't do it right, you can have very noisy switch mode supplies. So we have extensive expertise in package design. We do a lot of different types of modeling to make sure that the AC current paths are inside the package. Also, we design the magnetics and the packaging for high reliability. And then the control loop topologies themselves, whether it be analog or digital, but especially digital, we spend a lot of time on the ability to optimize the performance of the device for the specific devices we're powering. So FPGAs or ASICs, the net result is small solution size, the high reliability, the high performance, and easy to use because it's a fully integrated device that you just add a few input and output capacitors and maybe some pin strapping.
Okay, Michael. So one of the things that I've seen talked about is the one Intel solution combining your FPGAs and your power solutions. Can you share some examples?
So if you look at a couple of examples, here is an ARIA 10 that's being used in an industrial or surveillance application. You can see the digital power SoC powers the core, and then we use what we call low VN power SoCs, analog power SoCs, to cover most of the other rails. So this provides you a very high efficiency but low cost solution that is optimized for this application. Another application, power tree for a radar application. This is based on a Stratix 10. So this particular solution uses the multi-phase controller and power stages for the core. So this applies the high current that's required for this, and yet still meets all the accuracy, transient, and ripple requirements for the core. And then we use a digital power SoC to create an intermediate bus, and then followed by our low VN small solution size, low cost, but high performance, what we just call power SoC, not a digital power SoC to power the other rails. Maybe one more example here. And this is for a 400 gig Ethernet switch test application. So this is another really important thing to bring up here in the choice of the control loop topology. And this is where the, application and the FPGA being an early part of the design methodology for the digital power SoC or the multi-phase controller is that in this tester environment, you wouldn't use a topology where the frequency changes based on load like a constant on time. So here we use it's a simple voltage mode PID control topology, but because it's digital, it has two-state operation. So in one state, it operates in a steady state mode where it's very low bandwidth to get very low ripple. And then it has the ability to detect when a load step, very early in the onset of the transient, the ability to detect the onset of a load step, switch to a very high bandwidth loop with nonlinear gain, respond very quickly to that load step so that the output voltage stays well within the regulation window without having to use a lot of bulk capacitors to hold that output voltage or to source the instant current that's needed during load step. And then once the load step goes away, it switches back to this low bandwidth loop. But it does this all at the same switch frequency. So we're able to change the loop bandwidth on the fly to meet the load step requirement without having to change the switch frequency. So this is another example of, using a digital control loop optimized for a specific application and, specific type of device FPGA where we're using this dual state or two-state control topology instead of something where the frequency changes around because the application can't tolerate that.
Now, is there anything else that you want to cover before we close?
The key points here are that this digital power SoC family and the digital multi-phase control plus power stages devices are designed to optimize for space, designed to optimize for fewer capacitors. Fewer of those bulk capacitors means better system level reliability. So you save space, you save cost, and you improve reliability. Because these are purpose-built for powering FPGAs and ASICs, they are optimized for those unique requirements. They're easy to use. So instead of taking, weeks and dozens of iterations, you can, have a complete design ready to go in very short order. It's designed in conjunction with and then validated with Intel FPGA, so you know it's going to work the first time.
All right, Michael, I really appreciate your time today. Designers tell us that power is one of the toughest challenges to get right, so hopefully our viewers can benefit from what you and your team at Intel are doing with Enpirion Power SoCs. And if you'd like to learn more about Intel's Enpirion products, click the link in the description or visit Mouser.com. And be sure to check back soon for the next episode of Tech Chats.